Okay, thank you, Christian. I'm happy to have this chance to give a PIPSAC talk. Sorry I cannot be there in person. So I will talk about mainly some ways in which symmetric functions can be used to solve problems in permutation enumeration. And I'm going to assume a basic knowledge of the theory of symmetric functions for my talk. Let's see, how do I? Oh, this. The arrow that controls the turning the pages is not doing anything. Okay, well, this works. Okay, so okay, as I said, the main goal will be to obtain some results on permutation enumeration related to symmetric functions. And some of the topics I'll cover are class multiplication in the symmetric group and connection with characters of the symmetric group, commutators and their connection with characters, alternating permutations and Folk's representation, Linden symmetric functions, and at the end, some generalization of descent sets. So at the beginning, it'll be more of a survey of known results, but at the end, I'll be doing some new results. Let's start with class multiplication, or how to multiply conjugacy classes. And the basic theory applies to any finite group G. Let's say we have conjugacy classes C1 up to CT, and let I and J be, well, two integers from 1 to t, the index conjugacy classes. So we can label the irreducible characters of G, chi1 up to chi t in some way. In general, there's no natural projection between conjugacy classes and irreducible characters. dr will be the degree or dimension of the rth character, and chi r super r sub I will be the character chi r evaluated at some element of the conjugacy class Ci. Now here's a basic theorem in the representation theory of finite groups. I think it goes back to Burnside. We're interested in how many ways can you choose an element in class Ci, an element V and Cj, so that their product is some, say, fixed element W and Ck. And this number will not depend on our choice of W. And here's a formula for this in terms of irreducible character values. This bar denotes complex conjugate, which is going to be irrelevant for the symmetric group, because all characters are integer valued. I can remind you, the way to prove this is to look at the center of the group algebra of G. Find this is generated by sums of the elements on conjugacy classes, and determine the irreducible idempotence for this center, and proceed from there. I won't go into details, but this is a standard result. Now we can reformulate this result for the symmetric group, Sn, in terms of symmetric functions. So let's let X stand for the infinitely many variables, X1, X2, etc., and similarly Y and Z. H lambda is the product of the hook lengths of the partition lambda of n. And then we have this identity, the sum over all lambda partition of n, H lambda, then the Schur functions, product of Schur functions, and S lambda X, S lambda Y, S lambda Z. Is this sum over all triples of permutations whose product is the identity in Sn. Well, this factor 1 over n factorial, and rho u is the partition, that's a cycle type of U. The sizes of the cycles are the parts of the partition rho U, and similarly rho V, rho W. So anyways, if you take the usual, if you take the coefficient on both sides of P lambda X, P mu Y, P mu Z, the power sum symmetric function, use the expansion of Schur functions in terms of power sums, you get exactly the identity I wrote on the previous slide. So this is just a restatement of it. But it makes it easy to do some computations if you put it in this form. So I'll just give one sample application. How many triples of elements are there in the symmetric group Sn such that the product of their squares is the identity? Well, if we divide by n factorial, it's just the sum of these hook length products over all partition of n. Curious result, but it's very easy to get from the previous identity I wrote down. If W is a permutation, we'll let SQW be the number of square roots of W. And we'll look at a linear transformation phi on symmetric functions over Q. It takes these symmetric functions to Q, the rational numbers, defined by taking any Schur function to 1. Now, P lambda has this well-known expansion in terms of Schur functions, whose coefficients are the irreducible character values of the symmetric group. So phi of P lambda, we set all these Schur functions equal to 1. We'll just get this character sum over mu, chi mu lambda. And again, this is well-known, follows from work of Frobenius. Also, you can prove it just fiddling around with symmetric functions, that this is the number of square roots of W, phi of P lambda. So I've restated this. Definition of phi of S lambda is 1. Phi of P lambda is the number of square roots of a permutation W of cycle type lambda. We take our identity here, apply phi separately to each set of variables. We have a phi acting on the X variables, the Y variables, and the Z variables. All these Schur functions become 1, so we just get the sum of the H lambdas. These P lambdas just become the number of square roots of U, V, and W. And so we get exactly the identity I claim. Well, you can do a little bit more sort of sophisticated symmetric function combinatorics and get further enumerative results about class multiplication in the symmetric group. In particular, it's a straightforward generalization that if we want the number of k tuples of permutations, this product of their squares being 1 divided by n factorial is just the sum of the k minus second powers of these hook length products. Okay, let me now look at another result that holds for all finite groups in which we can specialize as a symmetric group. So G is a finite group of order G. And for an element W of G, F of W will be the number of ways to write W as a commutator. That is the number of pairs U, V of elements in G, such that W is U, V, U inverse, V inverse. If IRR, your G is a set of irreducible characters of G, then it's a theorem in representation theory, not difficult to prove, that F is a class function, and we can write it as a linear combination of irreducible characters, and the multiplicity of the character chi, just the order of the group divided by the degree or dimension of the character. A curious result. So in particular, it's a theorem in representation theory that the order of a group is divisible by the degree of its character. that doesn't have any very simple proofs. The standard proof uses algebraic number theory. But it follows from that this f is an actual character. This coefficient is an integer, so it's obviously positive. So someone could find some direct proof that f is a character by finding a action g with this character. And you'll have a new, very interesting proof that g over chi of 1 is an integer. Even for the symmetric group, it's not known how to do this. Okay, well, we can restate this identity in terms of symmetric functions when our group is a symmetric group. And it just becomes this theorem. This 1 over n factorial times the sum of all u, v, and Sn. The power sum symmetric function of the cycle type of the commutator of u and v. We write it in terms of shear functions, and the coefficient of S lambda is this hook length product H lambda. So here's a sample application, maybe the simplest one that we can get directly from this theorem. Suppose we're interested in the distribution of the number of cycles of a commutator. In other words, if we let kappa W be the number of cycles of a permutation W, then we're looking at this sum 1 over n factorial, sum over u, v, and Sn, q to the number of cycles of the commutator of u and v. So this is a generating function for the distribution of the number of cycles in the commutator. And it just has this curious formula. Sum over all lambda partition of n, product of all, well, squares t in the diagram of lambda, the product of q plus the content of t. It's very easy to prove from this identity, knowing symmetric function theory, just that q of the xi is equal to 1. This p just becomes q to the number of cycles of w. And we know what this specialization is for this symmetric function S lambda. It's just this content product divided by H lambda. So the H lambdas cancel out, and we just get this product. So one can play a lot of other games about the numerative properties of commutators using this identity. But let me go on to the next topic, which has to do with the combinatorics of border strips or ribbons, certain skew shapes, and how they're connected with permutation enumeration. So let's let S be a subset of 1 up to n minus 1. The elements of S are B1 up to Bk in increasing order. Bs will be the border strip whose row lengths are these differences in the elements of S. We're beginning with B1 and ending with n minus Bk. And this sequence is a composition of n. So these differences are the row lengths of our border strip. And you know that by a border strip, we mean that the last entry of row I plus 1 is in the same column as the first entry of row I. Oops. Oops, I don't. So here's an example. B3, 4, 6, n equals 8. It's given by this border strip. It's a certain skew shape. Well, folks looked at the combinatorics of these skew shapes, and here's this very nice theorem that for any subsets S and T of 1 up to n minus 1, the scalar product of the shear function of the skew shape Bs with the shear function of the skew shape Bt is the number of permutations in Sn whose descent set is S, and the descent set of W inverse, the inverse descent set of W is T. So this is like the key to enumeration of permutations according to the descent set and inverse descent set. Well, let me just assume this theorem. We'll let beta n of S be the number of permutations in Sn whose descent set is S. Well, a theorem of Niven and then De Bruijn, and later give an elegant proof using the CD index, tells us how we can maximize beta n of S. What S maximizes the number of permutations in Sn with descent set S? That's just either S equals the odd integers between 1 and n-1. This corresponds to alternating permutations, or the even integers corresponding to reverse alternating permutations. So this led, result of Niven and De Bruijn led Ira Gessel to make the following conjecture. We're interested in not just maximizing the number of permutations with descent set S, but the number with a specified descent set S and inverse descent set T. That would be the scalar product. And Ira conjectures, or natural conjecture, that it's maximized when S equals T equals 1, 3, 5, etc., or 2, 4, 6, etc. The same sets S that just maximize beta ns, you repeat them to maximize the scalar product. Well, this is still a conjecture. One can use symmetric function theory in a very simple way to prove one little step towards it, that the maximum value of this scalar product is achieved by sum S equals T. Very simple. I mean, all we need is the fact that we can express this number, well, that this number, well, I've written it as a scalar product, but that its combinatorial interpretation has this scalar product formula. We just take the scalar product of the difference between these Schur functions, SBS and SBT, with itself, scalar product with itself. Of course, it's greater than or equal to 0 because it's a squared length of some symmetric function. So rearranging this inequality, using bilinearity of this inner product, we get SBS, SBS plus SBT, SBT is greater than or equal to twice this, SBS, SBT. Well, that means that one of these terms has to be greater than or equal to SBS, SBT. So that's the proof. Whatever SBS, SBT is, there's an S, either S, well, there's a scalar product where the S equals T that's bigger than or equal to it. But I don't know how to go on from there and prove Gessel's full conjecture. Now, this Folt's symmetric function corresponding to ribbon shapes becomes especially nice when we have a ribbon shape corresponding to alternating permutations. So let me recall the definition that W is A1 up to AN is alternating. If it alternatingly decreases, then increases, then decreases, etc. The descent set is 1, 3, 5, 7, etc. If En is a number of alternating permutations, En is called an Euler number. And I remind you of this famous theorem of André. The exponential generating function for En is secant x plus tangent x. Now, let's look at these ribbon Schur functions that correspond to the border strips, well, that of shape 1, 2, 2, 2, 2, 1, when n is even, they look like this, or 1, and then all 2 when n is odd. I would call them ribbon staircases. That's the boundary forms are normal looking staircase. You know, the dimension of this representation corresponding to this shape, the number of standard Young tableau of this shape is just the Euler number, En. If we look at the, so Rn will be this ribbon shape, this staircase border strip. Chi Rn will be the corresponding character of Sn, would not be an irreducible character. In other words, a Frobenius characteristic of this character will be this ribbon Schur function. Or another way of saying that is if we write SRN in terms of the power sums, P mu, we have our usual normalizing factor, Z mu inverse, and then the coefficient, the character chi Rn evaluated at permutation of cycle type mu. And Folk showed another nice result of his. Well, I just stated for n odd, it's a similar result for n even, slightly more complicated. But if n is equals 2k plus 1, then all the character values of this character are either 0 or plus or minus Euler numbers. Well, it doesn't really matter for this talk exactly what this number is, but it's plus or minus some Euler number. And let me give a sample application of Folk's theorem. Let me let LT denote this power series, 1/2 log 1 plus t over 1 minus t. Now we're interested in f of n, the number of permutations in Sn, such that both W and W inverse are alternating. What can we say about this number? Is there some kind of generating function for them? You know, if just W is alternating, then we get this secant x plus tangent x generating function. So here is the theorem, a very curious looking result, that we can look at the generating function, just the ordinary generating function for f of 2k plus 1. Remember, this was the number of permutations in S 2k plus 1, which are alternating and whose inverse is alternating. This is the definition up here. It's given by this sum. Euler number squared, this power series, L of t, the 2r plus 1 power divided by 2r plus 1 factorial. So how do you prove such a theorem? Well, let's let OP be the set of partitions of n with odd parts. I see, I think I forgot to explicitly say this theorem of Folk's. Well, I can say it now. Now in general, f of n, well, it's a general result yes, the scalar product of, maybe I skipped the slide. There's this other theorem of Folk's, and for any ST subsets of 1 up to n minus 1, the scalar product of S of the border strip shape corresponding to S and the border strip shape corresponding to T. I think, I must have pressed some button that skipped through a lot of slides. Let me go back to this definition. If we have any subset of 1 up to n minus 1, whose elements are B1 up to Bk in increasing order, the border strip whose row lengths are the differences in these elements of S. So the numbers B1, B2 minus B1, etc. It would be a shape like this when B is 3, 4, 6, and n equals 8. We have 8 squares in all, and the row lengths are the differences in these numbers. The end of each row is just below the beginning of the previous row. That means it's a border strip. Folks showed that these border strips are skew shapes, so we can look at the skew shear function, S corresponding to the border strip BS and SBT. And the scalar product of these two skew shear functions is the number of permutations in Sn with descent set S and descent set of the inverse permutation T. I don't know how somehow my computer skipped a whole bunch of slides, but okay, let's try to pick up from there. So we have so I've defined these border strips or ribbon shapes corresponding to a set S. The row lengths are the differences in the between the elements of S. And Folks, another nice theorem of Folks and Niven and De Bruijn is that the scalar product of the shear function corresponding to the border strip BS and the border strip BT is just the number of permutations with descent set S, whose inverse permutation has descent set T. Inverse descent set T. Now, we can let beta NS be the number of permutations in Sn whose descent set is S. Okay, yeah, so I went through this slide already. I think I skipped some other stuff. Okay, well, let's go back to the proof of this theorem of about this generating function for permutations which are W and W inverse are both alternating. It has this curious statement. So by the general theorem of Folks, this number Fn will be the scalar product of S of the ribbon shape Sn with the ribbon shape Sn with itself. These buttons that advance the slides are not working correctly on my computer. They skip all kinds of slides. I'm sorry for this. I don't know what's going on here. Well, let's see, to prove to prove this theorem, let's let OP be the set of partitions of n with odd parts. Then Fuchs's theorem about the scalar product of any two border strip or ribbon Schur functions, namely that they equal the number of permutations of a given descent set, and whose inverse has a given descent set, tells us that Fn will be the scalar product of the Schur function corresponding to this ribbon shape Rn, this shape here, ribbon staircase shape with its set. So we write this Schur function in terms of the power sums. The coefficients that we know are the character values for this skew character corresponding to this skew shape Rn with itself. And so by the orthogonality of the power sums, we're going to get this formula for f of n. And now we use Fuchs's theorem on the value of this character corresponding to this ribbon staircase shape. All the character values were 0 or plus or minus Euler numbers to get this formula for f of n. It's the sum over all partitions with odd parts, partitions then with odd parts, z mu inverse, and times the Euler number e2r plus 1 squared, where r was actually I think, yeah, 2r plus 1. Remember, n is odd here. 2r plus 1 was the number of parts of the partition mu. Well, once we have this number, it's just, I say, generating function manipulatorics to get it into this generating function form that I stated before. Okay, let me go on to the next topic, which is Linden symmetric functions, and look at their applications to permutation enumeration. I hope the slides behave better. So for a partition lambda of n, k lambda will be the conjugacy class of Sn, consisting of the permutations of cycle type lambda. And now we're going to be looking at also Bessel's fundamental quasi-symmetric function indexed by subsets S of 1 up to n minus 1. And remember the definition, Fs is the sum over all weakly increasing sequences of integers, positive integers, I1 up to In, with a strict increase required if at the ij, if j is in S. The product xi1, xi2 up to xin. This is Gessel's fundamental quasi-symmetric function. And now we'll look at the Linden symmetric function, L lambda, and I'll define it as follows. We look at all permutations of cycle type lambda in this conjugacy class of cycle type lambda. The Gessel quasi-symmetric function corresponding to the descent set of W. Now, a priori, this is just the quasi-symmetric functions, some quasi-symmetric functions, but it's a theorem that it's a symmetric function. So I'll call it the Linden symmetric function. Here's an example. The conjugate state class 2, 1 in S3. This conjugate state class has 3 permutations. The descent sets are 1, 2, and 1, 2. So we're looking at the fundamental quasi-symmetric functions F1, F2, and F1, 2. And indeed, its sum is a symmetric function, S21 plus S11. So in fact, here's a theorem due to Gessel and Weitenauer. We don't quite state it like I'm doing here, but it's equivalent, that this L lambda is indeed a symmetric function, this Linden symmetric function. And you can compute it as follows. Ln is this sum of power sums. The coefficient is the usual Mobius function, UD. The sum over all partitions, D of n. I should say this Ln, this is known to be the Frobenius characteristic symmetric function of the induction from a cycle of length n to the full symmetric group of the primitive character of the cycle. Oh, I say that some induced character, which implies it's sure positive. The point is that we know this is sure positive. One reason being that it corresponds to an induced character. Well, this just defines it on partitions with 1 part n. To define it on a partition with k parts equal to n, this is what makes it difficult to work with these Linden symmetric functions. It's a plethism of the hk with Ln. And finally, for an arbitrary partition with k1 parts equal to 1, k2 parts equal to 2, etc., it's just the product. It's just the product of the ones on the parts separate. L1 to the k, L2 to the k, L1 to the k1, L2 to the k2, etc. So some facts about these Linden symmetric functions. They're sure positive because Ln is an induced character, so it's sure positive. Hk is a symmetric function, so plethism is sure positive. Multiplication preserves sure positivity. So this is a sure positive symmetric function. The sum over all partitions of n of L lambda is the regular representation, P1 to the n, but they're not linearly independent. It's a nice open problem to find the dimension of their span, or let's say the codimension inside all symmetric functions of degree n. Here's what these numbers look like up to n equals 15, codimension of the span of the L lambdas for lambda partition beta. And nobody has seriously looked at this question. That's just an aside. Now, a consequence of this Gessel-Weitenauer theorem on interpreting this L lambda in this way is that if we take lambda a partition of n, S a subset of 1 up to n minus 1, and look at the scalar product of this Linden symmetric function with the sure function of whose shape is a border strip corresponding to the set S. And this is just the number of permutations at Sn of cycle type lambda and descent set S. So this is the way of, the key to enumerating permutations according to their cycle type and descent set simultaneously. So for instance, we can get a lot of nice permutation enumeration applications from this theorem. For instance, Gessel and Weitenauer show that the number of involutions in Sn with descent set S equals the number of involutions in Sn of the complementary descent set S bar. course, this is trivial for all permutations, but for involutions, it's not clear what to do. You can't just write the permutation in reverse order. It will no longer be an involution. Well, how would we prove this? Well, the set of involutions in Sn is a union of conjugacy classes. And therefore, we can write it, well, and it's known that the sum over all involutions in Sn of the Gessel quasi-symmetric function corresponding to the cycle type of W is this product. In other words, it's just the sum of all S lambdas, where lambda is a partition of N. Well, this W is invariant under the involution omega that takes the S lambda to S lambda prime, because this sum, contains an S lambda and S lambda prime. Moreover, the involution that takes S of the border strip shape BS to the complementary set S bar. So omega takes this border strip Schur function or ribbon Schur function BS to BS bar. So knowing these facts about symmetric functions, we'll just take a look at this inner product by Gessel-Reutenauer. This is going to be exactly what we want, the number of involutions in Sn with the sense set S, because this sum of the Schur functions is just the sum of the f of rho W's for all involutions W. So this is going to be this number we want, the number of involutions in Sn with the sense set S. The scalar product is invariant under omega. So omega is just going to fix this sum. And it's going to take omega SBS into SBS bar. So that's the proof. The scalar product equals this number of involutions in Sn with the sense set S. This is the number with the sense set S bar. Well, let me give another application of this Gessel-Reutenauer theorem to alternating permutations. Let's Fn be the number of permutations in S2n of cycle type 2, 2, 2, 2, so all the cycles of length 2, and the sense set 1, 3, 5, etc. In other words, Fn is alternating. So we're looking at Fn as the number of alternating fixed point free involutions. So it's going to be the scalar product of this Gessel, this Linden symmetric function, 2 to the n, because we're looking at permutations of cycle type, all cycles of length 2, and the Schur function corresponding to the ribbon Schur function of shape 2, 2, 2, 2, 2, 2. This will be a special case of Gessel-Reutenauer. But L2n, by definition, is a clefism of Hn, but with L2, which is just 1/2 P1 squared minus P2, which is a half P1 to the 2n minus P2 to the n. And so now we put all this together, and with quite a bit of manipulatorics, as Adriano Garcia would call it, we finally get an explicit formula well, explicit in a way, formula of this number Fn. Take the power series 1 plus t, 1 minus t to the e squared plus 1 over 4. And expand it in terms of a power series in t whose coefficients are polynomials in e. This omega means that we now take e to the k and we move this k downstairs to become the Euler number ek. And that'll give the generating function for these Fn's. A very curious result. The usual statement of it is looks very complicated, but we can put it into this elegant form, sort of umbral form. This operation of turning e to the k into ek is an umbral operation. Let me just show you exactly what it means to compute this omega to the 1 plus t over 1 minus t to the e squared plus 1 over 4. Well, we first expand 1 plus t over 1 minus t to the e squared 1 plus 1 over 4 in a power series in the t's, whose coefficients are polynomials in e. It'll be this. Now, when we apply omega, we just bring these exponents downstairs. They become Euler numbers. That's the numbers in blue, where I've substituted, for E4 equals to 5. And so we'll get this power series. For instance, the coefficient of t squared is 1. That means there's a unique permutation in S4 that is alternating and has cycle type 2,2, not 2,1,4. Well, we can also do some nice descent set enumeration in the alternating group using this theory of Gessel and Reutenauer. I guess I don't have time to go into details here, but at least I can state the result. Let's suppose AN is the alternating group of degree n. And gamma n of S is the number of permutations in Sn whose descent set is S. I mean, we would expect this should be about half the number of permutations in Sn with descent set S. You'd think the property of being an even permutation or an odd permutation would not be strongly coupled with what the descent set of that permutation is. So we just divide by 2 the total number of permutations of the descent set S. Well, this Linden symmetric function theorem of Gessel and Reutenauer is well suited to look at the alternating group. We just have to sum this L lambda over all lambda, which are cycle types of even permutations. Or in other words, whose sign epsilon lambda of the corresponding permutation is even. So we need to evaluate this scalar product. And I skip some details of the proof, but at least here is the theorem, a surprisingly simple formula for the sum of all Linden symmetric functions L lambda, for which lambda corresponds to an even permutation. It's just, if n is even, it's just this simple sum only involving P1 and P2, and if n is odd, it's this. Well, as I don't have time to go into the details, I'm sorry, but as a corollary, we can compute the number of permutations in the alternating group AN, whose descent set is W, in terms of the number of permutations in Sn with a given descent set, whose descent set is S, whose descent set is also specified. When N is even, well, here's the number of permutations in Sn with descent set S. We'd expect it's about 1/2 of that number. But there's a little correction term. The number of permutations in Sn over 2, that is an Sm, with a certain specified descent set, which I've denoted S over 2, which I've defined here, but this sort of explains how you can divide a ribbon shape into 2 pieces times psi. So there's a certain small correction term. And when n is odd, we get a similar but more complicated formula. So we can use this nice Gessel-Weitenauer theorem to compute permutations. Okay. So I guess this is would be a good time for me to stop my talk. Thank you.
Sorry, I'm muted. Thank you very much, Richard, for a wonderful talk covering so many different and very interesting aspects of this topic. So I see a question in the chat from Dan Romick. First of all, if there is some explicit representation of the umbral operator that you showed in terms of some kind of integral transform, for example.
Oh, which umbral operator?
The omega, that one.
The one that converts powers to Euler numbers.
Right.
Oh. I don't know the answer to that question.
If I may say something, it simply means that you map a power of a variable to Eulerian numbers. So I guess you find, which means that it's these Eulerian numbers are moments under this map. So that is, you have to go to the orthogonal polynomials literature and look for the orthogonal polynomials which have the Eulerian numbers is, I think they are known, but I don't know them right away.
Okay, thanks.
Yes, other questions? Alejandro? You're muted.
Thank you. Yeah,
okay.
There's a question if maybe tying with at the beginning and the end of the talk, if Linden symmetric functions can be used to study factorizations of permutations with descent sets. Like you mentioned, yeah.
Isn't this more for Solomon-Smecke formula?
I'm trying to think.
Maybe like, is there anything, if you take the product of two of these lambdas, like is there some, you mentioned they're not a basis, but maybe the product, is it interesting? But thank you.
Yeah, I don't know. I can't answer the question now. It's a good question. Mm-hmm.
Okay, any other question? Okay, so if there are no other questions, then thank you so much, Richard, once again.